Well, thank you, Nigel. Welcome, everybody, for the second talk this afternoon. Let's start straight away with having an overview of what I will talk about today. We'll give you an overview about the status of exoplanet detection and characterization with a focus on what we know about small, rocky, and terrestrial planets, following up what Eva already told us this afternoon, and then discuss the factors which are relevant for habitability and how to detect atmospheres of extrasolar planets. But before we go to the planets around other stars, let's first have a look to our own solar system. And this plot is showing you the system, the planets in more or less the correct size range, of course not the distance range to the Sun. And we see the inner part of our solar system is characterized by small rocky planets, the terrestrial planets, followed by the gas giants and the ice planets at the largest distances. And this is typical for our solar system. Eva has shown you that extrasolar planetary systems have quite different architectures. The only planet with life in our solar system is Earth, and you can see it's on a rocky planet, and therefore we expect life and habitability to develop on other rocky planets and not on gas giants. This slide gives you an overview about the atmospheres of the terrestrial planets in our solar system. So we have here Venus, Earth, and Mars. And the atmospheres of these planets are quite different. Venus has an atmosphere dominated by carbon dioxide, but at very, very high pressure, 90 bar, and very high surface temperatures, more than 700 Kelvin. And therefore the conditions on Venus are far too hot to be habitable. We don't find water on Venus, and certainly not surface water. Mars, on the other hand, is a planet which also has a CO2-dominated atmosphere, but this atmosphere is very thin, and surface temperatures are very cold due to the thin atmosphere and its distance to the Sun. And again, Mars is a planet which is too cold for water to be habitable, to be present and the planet to be habitable. So the only planet where we find liquid water is Earth, with 1 bar atmosphere and nice and comfortably 288 Kelvin surface temperature. If you look at the atmosphere composition of Earth, it's not what you might expect, CO2 dominated, might expect from looking at the other two planets. Instead, we have an atmosphere dominated by nitrogen and oxygen. And the reason why we have this surface composition is very clear. It's because Earth has developed life, and it has developed oxygen-producing life during its history, which shaped the atmosphere of the planet as we see it today. So the only planet in the habitable zone of our solar system is Earth. Let's have a brief look on what is the habitable zone. The habitable zone is defined as the region around a star, the distance region around a star, in which a terrestrial planet can maintain liquid water on its surface. The surface is important here because, as I said, we believe planets need a surface to develop life, and life on Earth has developed on its surface, not in the interior and not in the atmosphere. And that also restricts, of course, the kind of planets where we search for life outside our solar system. It restricts it to small terrestrial and rocky planets with an atmosphere. This diagram is showing, wrapping up what I just said. It shows a phase diagram of water. Here's a phase curve of water, ice, vapor, and liquid. And you see Mars is in a region with low temperatures, low pressure, where water is present in the form of ice. Venus is at very high pressure, high temperature, and we cannot find surface water, liquid water on its surface. And only Earth is in the right temperature and pressure range, where we find water present in its solid form as ice, liquid, and vapor in the presence of clouds. And the question is, if we look for exoplanets, where in this phase diagram would they fall, and would they fall in the right range to have liquid water? If we look at this diagram, it's a very famous diagram in exoplanets, coming from Jim Casting in the beginning of the 90s, and it's showing the classical habitable zone. To the left here on the y-axis, we see the masses of the star, the central star of planetary systems, normalized to the mass of the Sun. So the solar system is up here, here's the Sun, and here's the orbital distance of planets. Here's the solar system: Mercury, Venus, Earth, Mars, and Jupiter. And the blue region here marks the distance range of the habitable zone in our solar system. You might wonder why Venus and Mars are more or less included. Well, this is because they might have had habitable conditions in the early solar system, although they are not habitable today, as I just said. So we have this distance range, which is habitable for a solar type G-type star. However, if we go to stars with smaller masses, they also have less luminosity, so less energy that arrives at the planet, and therefore the habitable zone moves closer to the star. This is shown here in this equation given by Jim Casting, showing the distance of the habitable zone, and it scales with the luminosity of the star. So for stars with less luminosity, the habitable zone moves close, and you can see it moves very, very close to the star, to up to 0.1 astronomical units and less for very cool M-dwarf stars. The distance range here, this line, marks the tidal locking range. That is the distance where planets that are closer inward might be tidally locked. That means they might always face with the same side to the central star due to gravitational interaction with the star. And we might come to that later. So what is governing the borders of the habitable zone? Well, in the inner habitable zone is limited by the so-called runaway greenhouse effect. That means if we take the Earth, it's a short experiment, you take the Earth and you move it closer and closer to the star, of course it becomes hotter and hotter, and water will evaporate, the oceans will start to evaporate, and water, being a very strong greenhouse gas, means the temperature on the planet will rise even further. So this process will go on until all the water is evaporated and eventually lost to space. And then you will arrive at a planet like Venus, for example. On the other hand, if we move the Earth out, away from the sun, it will start to freeze, become colder. All water will be condensed in the form of ice, leaving CO2 in the atmosphere, which eventually might also freeze. So the outer limit of the habitable zone is governed by CO2 and by clouds in the atmosphere, which can change surface temperatures and have an influence here on the outer edge. So the inner edge is governed by the runaway greenhouse effect, and the outer by freezing. Now, having had a look at this in the solar system, how about other habitable worlds? In particular, if I come back to this, are there planets around cooler stars in the habitable zones, which might also show life as we find it on Earth? So this diagram just shows and illustrates the wish of mankind to look out and find other planets. How do we do this? This list gives you an overview about the different detection methods that are used. There's direct imaging, and Eva just showed you a nice example of a planetary system detected by direct imaging. Radial velocity shows the movement of the central star induced by the planet. I'll come back to that in a minute. Astrometry is essentially using the same information, but measuring position on the sky. Microlensing is the detection of planets by gravitational lensing. You can do it by timing of pulses, for example, from pulsar planet or variable stars, or measure the reflected light of planets. I don't want to go into detail of all these detection methods. I just want to highlight two methods, the radial velocity and the transit method, because they are not only the most successful today, but they also provide us with a wealth of information about the planet and its characteristics. So in this plot to the left, this is showing you the radial velocity method. The radial velocity method measures the position of the movement of the star. Here is the orbit of the planet. The planet itself we cannot see; it's too faint to be seen directly. But it's inducing a wobble of the star around the common center of mass, which is indicated by the cross here. So as the star moves around the common center of mass with the period of the orbiting planet, the star moves towards us and away from us, and therefore its light is blueward and redshifted. And from this shift of wavelengths, we can determine the velocity of the star, the radial velocity component of the movement of the star. This gives us the orbital period of the planet, it gives us the distance of the planet to the star, and it allows us to determine a minimum mass limit of the planet. So all planets which have been detected by the radial velocity method provide us with the orbit parameters and a planetary mass. However, with a limit n sin I. The sin I means the inclination, the orientation of the orbital plane of the planet in the sky is of course unknown, and therefore we have this sin I uncertainty here, which means the planet could be higher than determined by the radial velocity method. The transit method uses another technique. The transit method can detect planets which transit in front of their star. That means we see the orbital plane of the planet edge on. So this is the orbital plane of the planet. The planet comes here. It moves around the star. It moves in front of the star. When it's in front of the star, it shades some of the stellar surface. Therefore, if we measure the brightness of the star over time, as shown here, the brightness of the star is more or less constant, but if the planet moves into the line of sight, it shades some of its surface and the brightness drops and goes back to the value before as the planet moves out of the line of sight. The drop of the intensity is of course proportional to the size of the planet. Larger planets cause a larger drop than smaller ones. And so it's immediately clear from this method we can determine again the orbital parameter from the orbital period of subsequent transits. But we also know the inclination, we know the orientation of the orbital plane, because if the orbital plane is not oriented more or less 90 degrees, we don't see a transit. And from the drop of intensity, we can determine the planetary radius. So we have two methods. One detects the planet and it gives us its radius. The other one detects the planet and provides the mass. If we put the two together, we get the true mass and the mean density of the planet. We get even more. You can imagine there are certain options for false alarms. For example, in the case of the transit method, it could be eclipsing binary stars. In the case of radial velocity, there's the n sin I uncertainty, and we don't know the size of the planet. So only for planets where we have both measurements, we know what we have. We know the mass and the mean density, and we call these objects secured planets. And if we are lucky and the transiting planet orbit very bright stars, then we can get a number of additional parameters. For example, we get the mass and mean density very precise. We can constrain the inner structure and composition of the planet. We can determine the spin-orbit alignment, the effective temperature and albedo, and even the atmospheric composition of the planet, as I will show later. This plot gives us the detection status as it is more or less today. On the y-axis, we have the mass of the star, and here the orbital distance. Our solar system is indicated: Mercury, Venus, Earth, Mars, and here the gas giants and ice planets. And all the dots, all the colored dots, correspond to detected extrasolar planets by the various techniques. Red dots with downward arrows indicate planets which have been detected by the Kepler mission, the Kepler satellite missions, from which we are sure they are planets. We can exclude the option of eclipsing binary stars, but we don't know the mass very precisely, so this is upper limits on the mass. What you can see here is that the range of Jupiter and Saturn-like planets is more or less well filled up to distances to 5 AU astronomical units. However, if we look here in the region of the terrestrial planets in the solar system, Earth and Venus, or even Mercury and Mars, we have no exoplanets here. Even when we come closer to the star in this range, there are no small rocky terrestrial planets detected yet. You might have heard about a number of planet candidates from the Kepler missions which fall into this range, even smaller than Earth and Venus. However, for these planets we have a radius, but we don't have a mass measurement. So we are not really sure if they are planets and which kind of planets where they would fall in this kind of diagram. And that leaves space, of course, clear here for future detections in the regime of terrestrial planets. Highlight from recent years were the first secured rocky terrestrial planets was like the Kourou 7b planet detected by the Kourou satellite. Just to give you an example how such measurements look like, here we see the transit light curve. It's the brightness of the star. It drops as the planet goes in front of the star and goes back to its previous level. And this drop corresponds to only 0.035%. To the right, you see the radial velocity curve made to confirm the planet and to determine its mass. And this is a planet with only 1.6 Earth radii and 7 Earth masses. So this is surely a terrestrial and rocky planet. This is what we are looking for. But it's orbiting the star at only 0.8 days. That means its orbital period is only 20 hours. And it's so close to the star, its surface temperature is around 1000 Kelvin, so far too hot to be habitable. Measurements, radial velocity measurements, have shown the presence of a second planet in there, which, however, is not transiting, and there may be even a third planet in the system. Interestingly enough, the Kepler satellite, now this Kepler satellite has detected a very similar system, the planet Kepler 10b. Kepler 10b is a planet with only 1.4 Earth radii and about 5 Earth masses, so again, a rocky terrestrial planet, but it's again on an orbit very close to the star, 0.8 days, so about 20 hours orbital period, and like Kourou 7b, it's far too hot to be habitable. And also this system shows a second planet orbiting further out. So it seems these kind of rocky planets with masses larger than Earth mass, which are called super-Earth planets, seem to be very, very common. To compare this to our solar system, we don't have anything like that in our solar system. We don't have planets inside Mercury's orbit. So recently, we heard the announcement of an Earth mass planet orbiting the stars closest to us, Alpha Centauri b. Alpha Centauri is a double star system, and one of the stars is orbited by a planet of only 1.1 Earth masses. This planet has been detected by the radial velocity method, so we don't have a size for this object. However, it is a milestone in the detection because its mass is so low, it's around 1 Earth mass. This has been an effort which required 4 years of observations to reach sufficient accuracy to get this detection. How is the planet in terms of habitability? Well, again, the planet has an orbital period of 3 days only. It is very close to the star, and again, it's too close to be habitable. So to sum this up, we are able to detect planets, rocky planets, in the mass range of 1 Earth mass and in the size range of 1 Earth radii, but the planets detected so far are far too close to be in the habitable zone. And this is illustrated here again for the case of Alpha Centauri b. For comparison, our solar system, Mercury, Venus, Earth. The gray shaded region gives the habitable zone for Alpha Centauri b. It's closer to the star than in our case, so Venus in this case would be in the habitable zone of the star, but the detected planet is shown here. It's far too close to be habitable. Another planet that made it into the press as a second Earth is Kepler 22b, a planet with only 2.4 Earth radii, orbiting in the habitable zone of this star. The habitable zone is given here as the green shaded area for comparison below our solar system. And this planet, Kepler 22b, is indeed in the habitable zone of the star. However, it's detected by Kepler with a very well-determined size, but we don't have a mass determination. We only have an upper limit to the mass, 35 Earth masses, and recent measurements have shown it's much more likely to be a mini-Neptune planet and not an Earth-like planet. But this planet shows that the detection of planets by transits in the habitable zone is possible. We just have to wait for the right object to come. This is another plot of the Kepler satellite. It's showing a histogram of the detected planets versus the planet Mars radii. So this is not only planets where masses could be determined, it's all objects with showing a drop in the intensity, showing regular transits. So all planet candidates. And if you look at the occurrence of these candidates, you see the number is rising towards smaller radii. It's leveling out here, and in the moment it's not clear if this leveling out is true, or if the number would increase further if the Kepler satellite could detect even smaller planets. So what is expected is a large number of small rocky planets orbiting around other stars. And this is strengthening the case to say, okay, there might be planets out there which would be habitable and orbit at the right distance even. But if you look at what we know today, this is again a diagram as you have seen it before. It's showing the mass of the star here. the distance of the planets, and now the green band shows the location of the habitable zone. We have again the solar system, Mercury, Venus, Earth, Mars, and the gas giants, and Earth, Mars, and Venus are in the habitable zone. If we take it over the history of the solar system, here the black dot is Kepler-22b, indicating again that it would be in the habitable zone, but unfortunately it's too heavy, it's a mini-Neptune planet. All the other stars are terrestrial exoplanets with masses less than 10 Earth masses, so-called super-Earth planets, and you see most of them are far too close to their star to be habitable. But some of them, detected by radial velocity, fall into this yellow band. Thus, these are planets which might show habitability, or in principle could have liquid water on the surface. In particular, for planets orbiting M dwarfs, these are low-mass cool stars. The habitable zone is so close to the star that the detection of planets in the habitable zone is, of course, much easier than around solar-like stars. So what's the composition and internal structure of these exoplanets? Well, to understand what these planets are like, you have to look at the masses and the radii. This is shown here. This is a mass-radius diagram, mass on the bottom, radius on the y-axis, and the lines here show the mass-radius relationship for planets of different composition. Let's start with a pure ice planet. If I take a certain mass of ice, I get a planet with a certain radius, and if I increase the mass, of course, the radius of the planet increases as well. Planets made out of hydrogen and helium, so gas giants, are up here. Planets made out of rock and iron are down here, and here's the position of Earth and Venus. And you can put all the known exoplanets in this diagram and see that we have these cold and hot Jupiters, we find Neptune-like planets, and we find super-Earth planets like Kourou 7b. We zoom in such a mass and radius diagram as it's shown here, so we only look into the super-Earth mass range up to 10 Earth masses. We have the same kind of mass-radius relationships. So this purple line here is a planet that would be made out of pure iron. The red line is a planet that's made out of pure rock, and the blue line is a planet made out of pure water ice, and all the other lines are mixtures in between. And the squares with error bars here are the known extrasolar planets in this mass regime. And there you notice something surprising. For example, if you look here at 7 Earth masses, you see we find planets with the same mass, similar mass range, but almost a factor of 2 difference in radii. We have planets up here whose density is less than water ice. So how can this be? Well, this is explained by atmosphere. So these are planets which probably have an atmosphere around them, making them appearing larger than they actually are. But even here in this range, we have quite a large difference in radius for similar masses. And that tells us that the composition range of planets is much more diverse than what we would expect and what we would find in our solar system. So are these planets habitable? Well, if we keep in the super-Earth regime, what we find is planets which could have low densities, high water ice content, so something like ocean planets, but also rocky planets with a high iron core. And which ones are these habitable? This is just wrapping up where we are. We have about 800 extrasolar planets, many planetary systems. We have hot gas giants, hot super-Earths. We find planets around different types of stars, in particular M dwarfs. We find them on eccentric orbits, large orbital inclinations, but Eva talked about planet architectures, so I don't want to repeat this here. But if you wrap all this up, you see that planetary systems can differ substantially from our own solar system. And even the planet itself, the mean density, the internal structure, might differ completely from the planets we find in our own solar system. And this is a surprising message that we have got from exoplanets in the past years. So when we think about habitability, and we have to find planets in the habitable zone around solar systems, around other stars, well, let's have a look in our own solar system. In our own solar system, we have 2 objects which are in the habitable zone. One is Earth, which is certainly habitable, and one is the Moon, which is certainly not habitable. So it needs more than the detection of small objects in the habitable zone of stars to be sure that the planet is habitable alone. And in the second part of the talk, I would like to discuss what it takes to make a planet habitable and how we could detect that. So how do we know a planet is habitable? if it orbits in the habitable zone, that it's indeed an object which could develop life. Well, what does a habitable planet need? A habitable planet needs moderate surface temperatures to maintain the liquid water on its surface. It also needs an atmosphere to maintain the surface temperatures and to an atmosphere whose composition is suitable for life. And it must keep the atmosphere for sufficiently long time periods to develop life. The reason why the moon has not developed life is very simple. It has never been able to develop an atmosphere and maintain it. It's far too small, it has too low gravity. If you look at the Earth climate system, you find it is a very complex system which governs the climatic processes and the surface temperatures on Earth today. There's the incoming solar radiation, there's the water cycle, the exchange of water between the oceans and the atmosphere, clouds, which have an influence on the radiative transfer, greenhouse gases, atmospheric composition, the greenhouse gases heat the surface, heat the atmosphere, volcanoes as producers of also greenhouse gases like CO2, and the carbon cycle. So if you look at the next slide, it gives us an overview and a list of the climate relevant factors on terrestrial planets. And the most relevant factor is the central star, as we will discuss in the next slide. And in our case, the central star is a G-type star, shown here. So the spectrum of the sun is shown here in yellow, where this wavelengths, you know the spectrum peaks in the visible wavelength range. And this is the same for earlier and type stars, hotter F-type stars, but also cooler K-type stars, which again peak more or less in the visible range. But the cool M dwarfs, which are interesting because the habitable zone is so close to the star, they peak at much redder wavelengths at 1 micrometer, as you can see here. So of course, the luminosity of the star, but also the spectral energy distribution of the star, can have an influence on the surface, temperature of orbiting planets. Of course, the planetary orbit itself, the distance of the planet to the star, is key. It has to be in the habitable zone, otherwise it will be difficult to develop surface life as we know it. The atmospheric composition, in particular the content of greenhouse gases, is important. The biological activity, the example is Earth. In the case of Earth, the biological activity has modified the composition of the atmosphere. Atmospheric pressure, the difference between Venus and Mars, for example. We need sufficient pressure and sufficiently thick atmosphere to get surface temperatures for liquid surface water. The planet size and mass, they determine the scale height of the atmosphere, but they also determine the loss processes, gravitational loss of the atmosphere, the hydrological cycle, the geological cycle, and the age of the star. What I have marked here in red are the parameters which are in principle accessible to measurements of extrasolar planets, at least in the ideal case and with instruments being planned in the next years. What we have learned in the first part of my talk is that planets are very different. They are in very different systems to our solar system, and we might even see them at different stages of evolution. So the question is, how can we find out whether they are habitable? What we know is that rocky planets with mass, radius, and internal structure very different to Earth exist. We know that many of these planets, or detected planets, orbit different types of star, including the cool M dwarfs. And to understand if these planets could be habitable, we need a better understanding of the processes that govern habitability. So as a start to address this question, we can ask what happens if we place the Earth around another central star. For example, the M dwarf star, where the habitable zone is very, very close. These M dwarf stars are cool. They have an emission spectrum which peaks around 1 micron, much redder than the sun. But many of these stars are active stars. They show strong high energy radiation, and the planets in their habitable zone could be tidally locked. So very different conditions to the Earth orbiting the sun. Could the Earth, if we just take it and place it around such a star, remain habitable under such strange conditions? To address this, we have to make some assumptions, because at present we have not detected an Earth-like planet in the habitable zone for which we know the atmospheric composition. We know very little about these planets. As you have seen, the ones we have in the habitable zone around M dwarfs, we just have a lower mass limit. So we have to make some reasonable assumptions to address the question whether such planets could be habitable. And when we look at our solar system, well, a reasonable assumption is to assume the planets have a CO2-dominated atmosphere. We know Earth also had a CO2-dominated atmosphere at the beginning, and the atmosphere we see today is caused by life. So there are two choices. We can assume these planets have a CO2-dominated atmosphere, or we can assume they may have developed life as on Earth and take the modern Earth atmosphere. So let's, as a most simple example, assume the planet is an Earth twin. And that means it's orbiting its star, its M dwarf star, in the habitable zone. It is really like the Earth. It has the Earth composition, Earth size, Earth mass, and so on. And then we perform some model simulations of the atmospheric temperature profile, the chemical mixing ratios, and the greenhouse warming to see how does the Earth change if we place it around such a cool M dwarf. And then we can also calculate its spectral appearance and check whether this could actually be observed or not. Well, a pioneering paper trying this for planets around M dwarfs was done by Antigona Segura in 2005, who used a 1D photochemical model to compute the radiative transfer of an Earth-like planet in orbit around the M dwarf stars. So you see here again the input spectra that were taken of solar-like planets and here of M dwarfs in comparison. And here the resulting temperature profile. But what was done in this work was the temperature surface temperature here was fixed to 288 Kelvin. That's why they are all at the same temperature here on the surface. But if we look at the temperature profile in the atmosphere, where the temperature decreases as we go up in the atmosphere, for all planets it's an adiabatic decrease. If you look at the Earth around the Sun, then the temperature increases again, because here we have the ozone layer in the Earth's atmosphere causing heating of the stratosphere of the Earth. But the Earth around M dwarfs, these two different M dwarfs here, does not show such temperature inversion at all. And why is that? Well, this is caused by the ultraviolet spectrum of M dwarfs. These M dwarfs, although they are much fainter in the optical and infrared range than the Sun, this is very different in the UV range. They are much more active, changing the temperature profile of the planets. So what we've done is we have repeated these model simulation experiments, but we kept the incoming surface flux top of the atmosphere constant, and we let the surface temperature vary and adjust to this condition to check what influence does the spectral energy distribution of the star have on the surface temperature. And we get the same results as Antigona Segura in the sense that planets around M dwarfs don't show the stratospheric temperature inversion as seen on Earth. It differs a bit for different types of M dwarfs, but in general this is confirmed. However, when we look on the surface temperature, we find that the surface temperatures vary a lot, but they are always in the habitable range. That means if you place the Earth in the habitable zone around an M dwarf star, the temperature might be different. It may be 10, 20 degrees hotter than it is on Earth today. So on Earth it would be a catastrophe for sure, but in general it would not inhibit the development of life. So what are the factors, the dominant factors affecting habitability? Well, the dominant factor, as I said, is this total stellar energy input. It's the stellar luminosity and the orbital distance to the star. So wrapping this up, this means the planet has to be in the habitable zone at the right orbital distance according to each stellar type. And then there are second order effects, and these are the dominating effect here is the greenhouse gases. The amount of greenhouse gases in the atmosphere determines the surface temperature. There are modifications by clouds. Clouds can heat or cool the surface, which is very important for planets which are near the edges of the habitable zone. There, clouds can make a big difference. The stellar type itself affects the atmospheric chemistry. I've not gone into detail that in the last slide, but it does affect the atmospheric chemistry, but it does not have a big effect on the surface temperature. However, it can have a very strong effect on the visibility of biosignatures, as you have heard in the talk by Lee Grenfell before. And then there are a number of other effects which have not been studied yet in the context of exoplanets, the geological activity, the magnetic field, and so on. So how to assess whether a planet is habitable? How do we ever know? Well, first we have to find them. We have to find terrestrial planets. As you've seen, we don't have them today. So the first thing is to find planets with known masses, known radius, and known mean density. So we know they are rocky, we know their internal structure, at least roughly. They have to be at the right orbital distance, so within the habitable zone. And then we need constraints to second-order effects. We have to know if the planet has an atmosphere, if its gravity is sufficient to maintain the atmosphere for long time periods. Are there greenhouse gases that can heat the planet? Is the internal structure favorable to develop such an atmosphere at all? Is there volcanism? Is there tectonics, for example? Or a magnetic field which protects the atmosphere from losses? So all these parameters are, of course, difficult to constrain, and that means we need observations of an atmosphere to get some indications on these parameters. So how to do that? Well, this plot is showing a spectra of the terrestrial planets of our solar system. Here's Mars, Venus, and the Earth, and what we see is the flux in the optical near-infrared range and in the mid-infrared range, indicating the molecular absorptions we would see in the planets in our solar system. For example, here at 15 micrometer, we have a very strong carbon dioxide absorption line, which is visible in all three planets, even on Earth. Here we have the famous ozone absorption line, famous because it's used as a biosignature, as you heard by Lee Grenfell before. We have water absorption lines indicating the presence of water in the atmosphere of Earth. So, of course, this is something we would like to have for extrasolar planets as well. So, but how can we get it? And here again, transiting extrasolar planets play the key role today. The transit geometry is shown again here. So we have the star, the orbit of the planet. The planet transits in front of the star, the primary transit, and as it orbits around the star, it also disappears behind the star during its secondary eclipse. And that means we are able to separate the signal of the star and the signal of the planet. How do we do this? Well, for example, we can take a spectroscopic measurement while the planet is in front of the star. So the light of the star has to travel through the atmosphere of the planet to us. We can take a second measurement while the planet is on the side. In this case, all we get is the spectrum of the star. And by dividing one by the other, or taking the difference of one from the other, we can isolate the planetary atmosphere spectrum. Such a simulated spectrum is shown here in the case of the Earth around the Sun. So this is how the Earth atmosphere would look like during such a transit. And you can nicely see all the molecular absorption bands in the Earth's atmosphere showing up in such a spectrum. In reality, it is not a spectroscopic measurement, but spectrophotometric measurement. And that means the transit is observed at different wavelengths. And this is illustrated again here to the right. We have the flux of the star measured over time. So the flux of the star is constant. It drops while the planet is in front of the star and comes back again. However, here, if we do this measurement not in visible wavelength, but at infrared wavelength, where we see the emitted light of the planet, that means while the planet is here next to the star, we have the emitted light of the star plus the emitted light of the planet. And if the planet disappears behind the star, we only have the stellar light left, of course. And that means the difference here directly shows us the infrared flux of the star. In similar measurements, this is explaining the same geometry during primary transit in the visible range. And here we have the measurement, the light that is blocked by the planet alone. But if the planet is surrounded by an atmosphere, as shown here, it appears larger than it actually is. And that means it also causes a transit that's deeper. And by performing this measurement at different wavelength band passes, we can isolate atmospheric molecular absorptions in the spectrum. The strength of the signal is determined by the scale height of the atmosphere during primary eclipse. That means a more extended atmosphere with a larger scale height will cause a larger transit signal than a very thin and small atmosphere. In secondary eclipse, where we measure the infrared emitted flux, the signal is governed by the temperature of the planet. So hotter planets will show a larger signal. Examples are shown here. This is an example of a primary transit done in the optical range of a hot Jupiter planet. So here's the absorption shown over wavelengths. All the colored lines show different models of the Jupiter planet gas giant atmosphere. So there are models with water and methane present, water and clear sky, or water and hazes in the atmosphere. And the black crosses are the actual observations. You can see in the near-infrared range, it's rather inconclusive. All the models more or less overlap, and the error bars of the measurements are rather large, and it's difficult to disentangle the measurements, although one might say that the model with water and methane fits better here in this wavelength range. In the optical, however, it's very clear. The measurements are here, and they coincide with the model including hazes in the atmosphere of the planet, which is showing a clear indication that there are clouds present in the atmosphere of this hot Jupiter planet. Several of these kind of measurements have been done today to detect atmospheric molecular absorptions in the presence of hot Jupiter-like planets. But how about super-Earths? Because we are interested in habitability, so we are more interested in terrestrial super-Earth-like planets. But there are very few super-Earths detected so far where such measurements have been possible. The best studied super-Earth planet is GJ1214b. It is a planet with 2.7 Earth radii and 6.5 Earth masses, orbiting an M-dwarf star, GJ1214. And these plots just show as examples some of the measurements that have been made in the past years, with a fleet of instruments from the Hubble Space Telescope, Spitzer infrared satellite, ground-based telescopes at various locations. There is a huge amount of data available for the super-Earth so far, but the results are still inconclusive. No clear molecular absorptions have been detected yet. This is just illustrating how difficult it is to make these measurements at super-Earth today. So we have detections of molecular absorptions for hot Jupiter-like planets, but unfortunately not for super-Earth-like planets today. And why is that? Well, this is shown here. The y-axis here is the brightness of known extrasolar planets in magnitudes. The x-axis is showing the distance of the planetary systems to us. And what we see here is blue are planets detected by radial velocity, red are planets detected by transits. You see all the transiting planets are here at large magnitudes. That means they are very faint. And most of the transiting planets are far too faint to allow such kind of spectroscopic or spectrophotometric measurements. Only the planets shown here with crosses are planets for which molecular absorption lines could be detected in the infrared range, and they are all hot Jupiter-like planets. So what do we learn from extrasolar planets? Well, planetary systems can differ significantly from our solar system. This is something we already know. We know that planets, small planets, terrestrial planets, are expected to be very frequent. This we know from the candidates, from the 3,000 candidates of the Kepler satellites. But the masses, radius, and densities are only known for a very few of these terrestrial planets yet. So we have candidates where the parameters are not known, but terrestrial planets with well-known parameters are just a handful. We know that super-Earths in the habitable zone around stars exist, in particular around M-dwarf stars. But a second Earth, that means terrestrial planets in the habitable zone of the solar-like stars, has not been found yet. This is something that needs improved detection techniques. And the detection of atmospheres around terrestrial planets has to await first the detection of such planets, transiting planets, but around bright stars, which are sufficiently bright to give us a signal-to-noise ratio where these measurements can be made. So if you want to place our solar system into context, well, this is a way to wrap up where we are today. If we take the distance range, the orbital distance range, where rocky exoplanets have been detected up to now and mark it in our solar system, they would all lie well within the orbit of Mercury. So all the detected rocky planets today are very close to their star, too hot to be habitable, except some few examples around M-dwarfs. The distance range where we see rocky planets in our solar system is up here. It's going up to the orbit of Mars. And this distance range is so far completely unexplored for solar-like planets. So there's a lot of work for us to do in the future. We have to exploit the full Mars range down to Earth-sized planets and if we can, smaller. At distances of orbital distances which are large enough for planets to be cool, so cool we can have water on the surface, so planets in the habitable zone, and detect the atmospheres around these planets in future. Stop here.
So the question is about the radial velocity method of detecting. When we have this simple model with a star and a big planet, one big planet, then it looks easy. But when we have, for example, a few big planets contributing to this, to the motion, it looks not so obvious. So how do they handle the data? So how do they distinguish between different influences of different bodies into this motion?
Yeah. So if you get a radial velocity signal of a planetary system, and planetary systems up to 6, 7 planets have been already detected, the signal is usually dominated by the heaviest planet. So what is done is fit on the obvious signal to subtract the component of the heaviest planet, then take the residuals and fit another component, and so on. This gives first indication on the number of planets and on their masses, but then of course the data are fit by an n-body simulation.
So it's a well-developed technique then.
Yeah.
According to the statistics, there are 800 planets and about 600 planetary systems. So most of them are only one single planet.
That's right. That's right. Yeah.
Okay, thank you.
Yes, thank you for the very interesting section. And I would like to ask a small question about I was wondering just if there any connection between the type of the planetary system we have around some star and the metallicity of the star, and how strong this connection is. Can be, for example.
Indeed, there has been a lot of work done to see any correlation between the metallicity of the star and the presence of planets. It seems there is some indication that stars with higher metallicity have, larger likelihood to host a planet. Yeah. So this is of course dominated by the gas giants. All the our knowledge or the statistics of exoplanets so far is dominated by gas giant planets. And to increase these kind of correlations that you are asking for, so how is the planetary, not only the presence of a planet, yes, no, but also the presence of gas giants, rocky planets, how is this correlated to the stellar metallicity? is I think one of the key questions. But we need to increase the statistics of planets in the Neptune regime, the ice regime, and in the terrestrial regime to go deeper into this question.
Yes, thanks. And I would also still like to ask something related to geology, not necessarily observing, but I would like to know if you think that active tectonic system is necessary for the habitability in long term, and whether this requires certain size of planet, or what is the basic kind of requirements for maintaining tectonics?
Yeah, this is a very good question, and it's a question heavily debated here in-house in Berlin with our colleagues who work on planet interior, planetary tectonics. I'm personally not the expert in this, but I can tell you I can give you a wrap-up of our discussion here. That's all I can do. And so the general feeling here is that plate tectonics is certainly facilitating the development of habitability because you are recycling material in the carbon silicate cycle. I look at Lee here. He may also comment on this. He's more an expert than I am on these issues. But plate tectonics is key in the carbon silicate cycle, which is believed to stabilize climate on Earth. Plate tectonics is also causing volcanism. I mean, volcanism is enhanced in planets with plate tectonics, so providing greenhouse gases into the atmosphere, which again is facilitating the development of life. So the general feeling here, if I wrap this up and then look at Lee, is that planets with plate tectonics certainly have it a lot easier to develop habitable conditions. Whether it's completely excluded to develop habitable conditions on planets without plate tectonics, I'm not sure that such a statement such a strict statement can be made. But if I would have to decide where to look first, I would look for a planet with plate tectonics. And this is one of the reasons why we think it's very important to characterize planets very well, to get their mean densities, understand their interior structure, understand whether they could develop plate tectonics, and bring these measurements together with atmosphere measurements to see which atmosphere is actually present, is there an atmosphere present, and see how it all fits together and whether it fits with our current picture of how planets like the Earth work. But that's really a little bit dreaming. It's bringing us into the far future in terms of really proving it by data.
A little bit of a follow-up is that whether you need a certain size, minimal size of planet to create tectonic.
Yeah, as I repeat, I'm not the expert of this, so I'm I just hear what my colleagues say. I know from the literature there are contradicting results depending on the models and the physics included in the models, whether if you have larger planets it would be easier to make plate tectonics, or whether larger planets would have it more difficult to develop plate tectonics. So in the literature, I think it's not completely clear. There is some work done here by colleagues in-house where it seems to be there's a kind of optimum mass radius range for planets to develop plate tectonics, which fortunately is in the range of Earth, of course. So it's ongoing research. I don't think there is a general consensus on this yet. It is one of the current most exciting questions, I think.
Thanks a lot, Heike. A very interesting talk. I enjoy a lot. And I just would like to ask you about the observations of super-Earth atmosphere. You mentioned what are the difficulties. But can you cheer us up, saying what are the perspectives with new missions, new instruments, or just we need to wait to find out the right planet around the right star?
Well, Eva, as usual, you're asking the hot questions. This is a much investigated question in the moment. And What I have seen and what we have done and other groups have done is simulate these kind of atmospheres, simulate spectra, and then see which signal-to-noise ratios you could expect with various instruments. And when you look in the literature, what seems promising is the James Webb Telescope and the ELT, which could, for planets orbiting very cool M dwarfs, be just about in the range where something could be detectable. And that, of course, I personally believe is very, very promising and is one of the reasons why we want to better understand such planets around M dwarfs, because if that could be, if we could get data with the James Webb Telescope, for example, we can prove our models. And M dwarfs are very peculiar. I think planets around M dwarfs, it may not be just a scaled-down solar system where you just have the Earth around a cooler star and the rest just everything else just remains the same. We have to better understand the effect of these M dwarfs on the planets, like cosmic rays, high energy, the tidal locking. It's possible, and you know more about this as well, about the dynamic interaction. So planets around M dwarfs, I think, are very interesting, and these might be within reach with the James Webb.
Thanks a lot.
So thank you to both the speakers of today for the nice lectures. I have a question to both of them, since you are both, I think, involved in numerical simulations. So my question is, what is the contribution that the numerical simulations of the atmosphere or of the system formation can give to the observations?
Shall I answer first, Eva, and then you?
Okay, I think that for dynamics and formation of planetary system, simulations are essential, and they are coming into the game in every stage of the evolution of the study. And you are asking about the observations, so I mean, you always need to test what is coming up from the numerical simulation with what you observe. So this is the sort of self. I mean, is the process which will need to be. I mean, interact itself. And so I would like to mention first of all that I mean already when on star planet formation stage in the computer laboratory we are doing the simple simulation of how the dust grains are stick together in order to build up the new to be a bigger body, and this is sort of maybe not observation, but the laboratory studies which are telling us if this process really can occur in reality. And indeed, there is very nice agreement between what is going on in lab and what is going in simulation at that stage. And the part which is more connected with what I said today during the lecture is this part which is starting with the gravity domination. And this is also, I mean, dominated by computer simulations because, I mean, you cannot really form and look how such bodies do evolve. And the enormous amount of parameters which you need to elaborate from the data also are based in the on the computing and simulations as well. That's important to say that we are looking for such I mean observations which will be able to really follow whole evolution from the beginning till the end. So, for example, the ALMA observation now are very valuable for what is going on in our simulations in order to really look at the very early stages of the planetary formation. So I mean, I cannot sort of imagine how we can do without. So the input into the understanding of numerical simulations is enormous, and observations are doing great deal of I mean, giving us a test what is really going on in the reality.
Yeah, I can only agree with what Eva said, and I think in the field of planet formation, theory is very advanced, and for example, planet population synthesis models, which give us a prediction about planet masses, densities, and orbital distances, and this is something we now have to testify with observations. This is why we make such a big effort to detect small planets at intermediate and large distances. Apart from the habitability aspect today, this is also important as constraints for model simulations of planet formation. And in terms of atmosphere simulation, I think it is very, very critical to continue these and understand the processes that shape habitability better, because the signal-to-noise ratio of spectra from terrestrial planets, that we will get in the next decades, hopefully, will always be low. And it will not be like getting a spectrum of Mars or Titan in our solar system. And we have to be able to interpret them very well, and that means we have to get a higher level of understanding what are the processes in planetary atmospheres in conditions that differ significantly from ours. And the question that was already raised about the link between atmosphere and interior, atmosphere of central star, the aging, what is the temporal evolution of the system, and the interaction of the with the stellar wind, stellar radiation for different types of central stars. All of this has not really been explored yet, and we need predictions from modeling now, also to find good targets to investigate observationally. I mean, to identify which are the most promising targets. Observing time is costly. We will not be able to do so many. And then when we have data, we need it for interpretation. So I think it's very, very important.
Okay. So do you think that also exoplanet moon could be habitable as well?
If you ask me if I think so, I think yes. Why not? If they have I mean, we have Titan in the solar system, so we know there are moons, or there can be moons with an atmosphere. If the central planet is orbiting in the habitable zone, and the moon has the right conditions in atmosphere, it could be habitable. But the detection will be very difficult, because then you have to not only disentangle the signal of the planet and the star, but you also have to you have to get out the moon signal from the star and the planet. So that will be very difficult. But coming and techniques are always improving.
Okay, thank you very much. Thank you.